Hello, welcome to the last session today. I'm Katja, this is Nico. We are both
Hello.
we are both working as data scientists at XING. I hope you all have a XING account and know what we do. So we aim to connect people professionally and to help them to find the right jobs. And in this talk, we will give you an overview over some recommender system challenges that we face. We will very broadly say something about algorithms. We will say something about the engineering, how can we do recommendations pretty fast online. And thereafter, and this is more or less the main part of this talk, we will tell you something how we deploy all these models that we use in our system on a regular basis and how we try to automate this part. So the running example will be job recommendations. So we have a lot of recommendations. The job recommendations and also the members you may know recommendations are the most important one. And in this talk, all our examples will deal with the job recommendations. So Nico starts.
Okay, so I start with the RecSys challenge and the algorithms. Just a small overview. First of all, let's look at what we have. So, like Katja said, we want to present the job recommender, and we have two use cases. Let's say mainly two use cases for the job recommender. First is user-wise. If we have a new job posting that is put on the platform, then the first thing that we want to do is find out, is this relevant to a user? And for a user, just find him the relevant job postings that he might like. So for example, here we have this person that from all the 800,000 job recommendations, job postings, sorry, that are on the platform right now, that they basically go through the job recommender and we filter out, here it's only 3 job recommendations, and you can see that this guy probably is a Scala developer or a Scala engineer because he gets these job recommendations. The second use case is for companies. They all have recruiters and they want to find new people. I think one of the most used buzzwords here at the conference is we're hiring, so you all know that. We want for the recruiters, if they, for example, say, I need some person who can develop in Scala and he maybe is a data scientist or so, I want to find the right persons for this guy. So those are the two use cases. Then let's have a short look at the platform itself. We have, first of all, we have the web app that you can see in the browser. And here, if you click on the left on the jobs tab, then what you see is jobs that we think you like, and these are actually the jobs that we recommend for you. And here, this example is Fabian Abel. It's actually mine and Katja's boss. And you see that he gets some data scientist recommendations. For example, the first one in Darmstadt, and then the second in Berlin, one more in Berlin, and another one in Berlin. So maybe this person, he likes to, he doesn't have a strong opinion on where he wants to work, but he wants to work as a data scientist or as a machine learning engineer. And then what we want to find is exactly these jobs that we think are the most relevant for him. Okay, and then we have 2 other, let's say platforms where you can also see jobs. One is mobile. We have an iOS app and an Android app. I hope you all have it installed and use it frequently. And then also you probably also know this if you're a XING user, we send push notifications via email. So sometimes in your email inbox, you have these emails, hey, we have new jobs for you. And so that would be the, let's say, third channel where you could get these job recommendations. Okay, then let's look at something that we like to call the triangle of contradiction. So we have basically 2 customers, as I've already mentioned. We have the users and the companies. And then the third entity in this triangle that you see is us, is XING. And basically all of these entities, let's say, they have certain demands or they have certain wishes on the platform. For example, the user, you don't want to get any job recommendation that for you seems like spam, and you want to have relevant recommendations. So let's say if you work as a data scientist, you maybe don't want to get something for Internet of Things developer or something else. Then we have the companies. If they want to search for candidates, they want to have relevant candidates, of course, and they want to have a high reach, so they don't want to just find 3 candidates, but many candidates, because maybe they like to choose among all of these candidates the best candidate themselves. And yeah, so this is the requirement for the companies. And then we have also us as XING, of course. Katja and I have to get paid, and yeah, so we have to get some revenue. So for example, we can get this by boosting the postings that are actually paid for by the persons or the companies that put these job postings on our platform. Makes sense, of course, because we all need to get money. And of course, as at XING, we also want to have happy customers. And so why is this called the triangle of contradiction? Because sometimes for a user, we have to push a posting that maybe is not, let's say, the perfect posting, but it's a paid for posting, and then we can get a little bit money if these guys click on it. And so whatever we do, we somehow have to optimize this triangle of contradiction. Okay, so let's look at what kind of data we have. So this, again, is Fabian Abel. We have 4, let's say, key sources of data where we get data from. One is the profile, so this is what you, as XING user, what you like explicitly state on your profile. So for example, your job, this guy is a data scientist, your skills, web science and data mining, maybe web science, okay, I don't know. Maybe, I hope he has more skills than these 2 if he's a data scientist actually. And interests, big data and Hadoop. So this is what you can put on the platform, what we make use of. Then we have the social network. So let's say you have friends on XING, I hope you do, or let's say members you may know, connections. And if you're also connected to a company, if you say I work here at this company, then we have these kind of social network connections that we can make use of. A third thing is the interactions. So if you use the platform, you click on something, you bookmark something, you rate something, you can actually rate the job postings that you get, so you should do that if you want to get better recommendations. And also the case if we show you recommendations, and let's say we showed you the same recommendation 3 times, for example, and what you do is every time of these 3 times you just ignored it. This also is some kind of implicit feedback that you give by not clicking on it. You say, this doesn't really interest me. So these interactions we have, and then of course we also have this also you could put as the social network, I would say, interactions of similar users. For example, we have other persons hopefully working as data scientists, and then if they click on something which seems to be interesting for data scientists, then what we can see is, okay, this person is very similar to this other person from the way of his skills, how his skills are set, and so on. So then we can basically find similar job postings, or no, we can actually, for a similar user, recommend the same job posting. Okay? And then we don't only have the user information, we also have information about the job posting, of course. So here is an exemplary job posting. What do we have? This is a data warehouse manager in Hamburg at Good Game Studios. So there you have the title, you have the company. We have the employment type. So here, this is a full-time job. It's not a part-time, not a freelancer job. Could be other kind of jobs. Employment type, sorry. And then, which is probably the richest description, is the full text description of the job. But also this is in a way unstructured. You have to find, let's say, keywords. If it mentions Scala developer a lot, or Java, or whatever kind of skills. So this is very unstructured, but we want to make, or we are making use of it, but it's just a little bit harder because it's not explicitly given, or it's not in a very structured way. And then if we go down a little bit, what we also have is other employees working at this company. So this example maybe is not the greatest one, because this is the CEO of Good Games. So if we ask him the question, is this a good employer, he would probably say yes. And also other, let's say, facts about this company, for example, social benefits, what you can get here, and the location where it's at, which is also very important. Okay, then let's have a look at how does our recommender system actually work. So like I said, we have 4 of these data sources, and these are all used to then basically, let's say, find a set of jobs or job postings which are relevant or which might be relevant. And then what we do is like a filtering on these job postings. For example, you could assume that a location-based filtering works in this way that if you work in Hamburg and let's say you've only been in Hamburg all your life, then maybe we don't want to recommend you a job in Vienna, for example, because we think this is not relevant because you're likely not going to move to Austria, okay? And then company filters, so you can actually also follow companies. So if you have followed a lot of companies, then maybe we think these are more relevant for you. Also career level, we don't want to give you a recommendation about basically, in German we say Praktikum, what is the English word? Internship, sorry, yeah. We don't want to give you an internship position if you're, let's say, on a very high career level and you've already been in a leading position. And then what happens in the end is a re-ranking of all of these jobs, and there we use a model called XGBoost, and I will say a little bit more about XGBoost in the end, but this model is then learned on real data. Okay, so here are some more of these strategies. I think I can maybe skip some of these because I already talked about it actually. For example, the content-based filtering. One more thing I can talk about is the item-to-item recommendations. So let's say you bookmarked something and then you bookmark the job posting because you're interested in it, and then you see, or we see, oh, there's another job posting, and from the job features, this is very similar to the posting that you have bookmarked already. Then what we do is this more like this approach. We assume that you're interested in these kind of jobs, and then you get more of these jobs. So that's one strategy, for example. And on the filtering, we can also basically turn it around. Like I said, this example, when you skip job postings 3 times, then we can also do like a less like this approach, for example, that because you have skipped this job, or let's say you can also actually explicitly say that this job is not good for me, then what we do is this less like this approach, because we assume then, this makes sense, you don't want these jobs. And then, some other strategies would be, for example, like I mentioned already, the company filtering, but we could also boost jobs where we know that in this city where this job is posted or where you would end up working, you have a lot of contacts because, maybe you like to be with your friends and then you're just more eager to go to this city. And then, I already mentioned that we have to boost the paid content because we need to get some money, of course. And then we also learn an outlier filter, which is actually also learned on like data where you interact with jobs postings. Okay, then we talk about engineering for recommender systems, and I will hand over to Katja.
Exactly. I will tell you something about the engineering and also what just happens in the background when we create the recommendations. So first of all, our tech stack, we are really huge fans of Scala, and we use a diverse set of tools and techniques. So we have a Hadoop cluster, we use Hive for calculations that can be done offline. We use Cassandra and MySQL as production databases. We use Kafka for messaging and so on. So what happens in the background when we want to create a job recommendation? So first of all, we provide a REST endpoint, and whenever we want to create or show the user a recommendation, the REST service is called with the ID of the user. And then in the back end, we have to gather a lot of information and have to do a lot of computation. And so currently we have we issue about 20 queries to databases we call other REST services, and we also issue 4 Elasticsearch queries. So if we would do all that sequentially, it would take several seconds, but we have the goal that the response time in at least 99% of the cases is below 200 milliseconds. So what we do is that we try to do as much as possible in parallel. So, and this is the internal structure of the recommender system, which is very similar to what you saw before. So the structure of this recommender service is similar in all our recommender services, but here again it's the example of the job recommender. So first of all, we get just the ID of the user. So we try to get information about the user. We need the job role, we need the career level, we need the friends, we need the interest profile of the user that is based on the activities of the user and so on. And when we gathered all that information, we give it to our sub-recommenders, and the sub-recommenders try to create recommendation candidates. Here, the recommender systems are more about the quantity, also about quality, of course, but more about the quantity. So, for example, we issue elastic search queries with the search queries with the explicit user profile. But we also use, for example, association rules. Like what Nico said before, if we know someone is a data scientist and there is a job posting that is especially popular among data scientists at the moment, this would also be done by one of these recommender components. So thereafter, we have the user ID and we have the IDs of a lot of job postings that might be suitable candidates. So again, we have to call a lot of data sources to get more information about these job postings. And when we have that, we then filter out, and this is where the quality comes into place. This is especially important for job recommendations, not even so much for people recommendations, because we figured that if you recommend a user a job that he doesn't like at all, like someone is a CEO and we recommend him an internship position, these users, they get really angry. We see that because we get responses, all in upper letter and a lot of exclamation marks. So we know they are really, like, I don't know, embarrassed, they feel misunderstood, so the filtering is really important. And yeah, so after the filtering, we have the final set of our recommendations, and then we have some rankers. As Nico said, we boost a little bit the paid content, we boost also jobs from cities where the user has a lot of contents, but we also properly trained a model using XGBoost on the implicit feedback data that we got. Okay, so to do all that within 200 milliseconds or possibly less, we have to use a mixture of online and batch processing. So we look up everything online that we can look up within milliseconds, and where it's also really important that we get the most actual information. Like if a user updates his profile and adds a new work experience, a new job title, it's really important that we directly react. Or if we get negative feedback, if the user says us, hey, I really don't like that recommendation or that kind of recommendation, we just have to react now and not tomorrow. We also pre-compute a lot of data. We do that whenever we need a more complete picture and when the computation would thus take minutes or maybe even hours. Examples are the interaction-based profile or also interest profile, where we for each user extract some skills, some job roles, some cities the user might be interested in based on the activity of the user. Also the association rules we just mentioned. Okay, and this is an example how it works, so for the association rules. So if we go to the bottom at the beginning, this is the part where we have an USI workflow that is scheduled to run every 30 minutes. And here we learn the association rules, like data scientists really like that job posting at that moment. And when we created these association rules, we export them to Cassandra. And then now we can go to the top. Then the REST service is called with the user ID. We first get the current job role of the user. So this is done in step 1. And then we have the recommender component who gets typical job postings for this job role by asking the Cassandra database. Okay, and now we go to the deployment of recommender system models. So we do a lot of stuff in the background and an offline calculation. For example, when the job postings come in, We crawl some job postings from the internet, but also we also have paid postings on our side. We categorize them. So usually when the postings are paid, we know the discipline from the company, but when we crawl them from the internet, we have to categorize them, and for that we use logistic regression. We enrich the job postings. We try to identify similar job postings. For that, we use a Doc2Vec-based topic modeling so that we can create an embedding for each of these job postings and can compare two job postings based on these embeddings. Yeah, we have the association rules. We really like our gradient boosted decision trees, so we use a lot of XGBoost. So for the outlier filtering, for example, we try to predict how a user would rate a job posting on a scale from 1 to 5 stars. And if we then figure, the user might only rate that posting with 2 stars, or maybe just even 1, we just kick the posting out. So here we have a regression problem. As I said before, we also have a ranking of job postings, which we trained using the implicit data. So did a user click on something that we recommended? Did a user just skip a posting several times, even if we recommended it very often to him? Here again, we use XGBoost, but we optimize the pairwise loss. So we have a lot of models. And all these models require that we create a ground truth, that we create features, that we evaluate the models offline, that we bring them into production, that we run an A/B test. But yeah, then we would like to be done, but we are not, because the data changes, people behavior changes, the website changes, so we have to retrain our models regularly. And this is what we do not like to do so much, like spending our time in retraining and not creating new models. So this is how we see the different steps, degrees of automation in ML, and we have almost all of them currently in our team. So on the first step, we have hacking, really handcrafted algorithms. We don't have them. This is where just a human comes and tries to make up some rules, like a data scientist always has Java skills. So you do not ask your data, you just make rules up with a human or a domain expert. So the human is pretty much involved, and I cannot recommend that. The next step would be algorithms based on data analysis. This is something we actually have in one or two challenges, where we don't have a ground truth, where we can't train a training set, but we can do some analysis. A human or a domain expert can make sense of the data, and this is where we come up with rules. But yeah, the human is pretty much involved here, and we have to do it again and again whenever something changes. And then comes the next step, where we have the machine learning with human supervision, where we say, okay, we can create a ground truth, we do feature engineering, we train models, but maybe someone is just doing that with a language that is not supported by our production system on his private on his private laptop. So we still can use the model in production, but we cannot just retrain it. We need the person who deployed it, created it the first time, and his laptop and his settings and so on. So that is also not so good. So the next step would be to have the ability to recreate new ground truths based on some scripts that you have, based on some logic that you created, and so that you just need to click on a button or issue a comment in the command line so that the model is just retrained. So you can say, oh, I have to retrain the model, and then you can just click your button and then it is retrained, and yeah, still, you have to check if the new model looks good or if something is fishy or some data changed. And then comes the machine learning with a high degree of automation. And this is actually where we aim to go and where we are already for two services, where we say, okay, we want to be able to schedule the relearning of our models. Like once a week, once a month, the model is retrained, it is evaluated, it is automatically used in production. So, and then there is also on the highest level, like the vision for the future where we can, where also features can be automatically constructed based on information about our database structure. But this is more like a vision. Okay, maybe that was a little bit abstract, so I can show you what we mean, what we want to do for all our services. So we are in the Hadoop world, we have our Hive service, and so first of all, we have to create a training and a test set. So for example, if we have ratings of users for job postings, this can be our test set. We know a user rated a job posting with 5 stars. And then we need to create features, like the job role of a user, the job role of the postings, the career levels, and so on. This can be done by just creating scripts that are scheduled to run like every 2 weeks. Using that, we train a classifier. And we do not only train one classifier, but several classifiers, because usually we have to deal with hyperparameters. This is something Nico will tell you more about on the next slides. So we learn several classifiers with different hyperparameter settings where we try to be really smart about picking the hyperparameters. And then we pick the best model. And this is stored in our model storage, just a database, where we now have the new model as a current model, but we also still have the previous model. And as I said before, it's still possible, that something fishy happened, like, a data who used to be filled is empty now or is not updated, so that the new model just behaves not the same as the previous model. So what we do here, and this is also done automatically, is that we run the service for 10 to 100,000 users, and we compare the results. Like, for example, the overlap of the same recommendations in the top 10. And they should be pretty similar. The results should be pretty similar because, the model was newly trained, but still it's, based on the same data, and it should be very similar. We also automatically create an A/B test, and we switch that A/B test on if these 2 models are not similar, so that we can compare them. And then we have the REST service that uses the model, and based on if the A/B test is on or not, it chooses another model. And then in the end, the human is still in the loop. So if an A/B test was started, we will check the results of this A/B test like after a day and then after a week to see if we want to accept the new model or not. Okay, so now Nico will tell you more about the hyperparameters.
Okay, thanks. So about hyperparameters, usually if you have done machine learning already, you basically just get a data set, you have some library, maybe let's say XGBoost, and what you do is you can actually just with a few lines of code just start this model and train it and see if something happens, but what you're actually doing is you're using the standard hyperparameters of XGBoost. So let me maybe go back one step. What are actually hyperparameters? Who of you would say that they know what hyperparameters in machine learning are? Okay, that is one hand. Okay, then let me go back this step. So let me talk a little bit about what are hyperparameters in machine learning. So hyperparameters are usually parameters that you have to specify before you learn the model. And one thing, it's you can't learn these from the data. That's the hardest thing, because what machine learners want to do, they want to have data and they want to learn everything from this data. But for these hyperparameters, you can't do it. And usually these hyperparameters, they, let's say, specify the complexity of the model. I also have 2 examples. So after this slide, you will see 2 examples. So let's say if we want to learn a very complex model or a very non-complex model, this basically crucially influences how good is my model. Do I overfit to the training data, or do I underfit? Can I generalize well? These kind of things. Then you specify how the model is optimized. For those of you familiar with machine learning, many people use stochastic gradient descent for, let's say, deep learning on images. This was not the greatest thing, or let's say you would at least use a little bit more than one image for your gradient, because that gradient would just pull the model too far away from what you actually want to do. And so Also in deep learning, yeah, you have all these other optimizers like with the Nesterov, with the step size adjustment, ADA-grad, ADAM, and so on, ADA-delta, all these kind of things. Then how the model is regularized, usually, so they're for like linear regression models, they are very simple regularizations. Regularization means you basically tell the model to not like 100% represent the training data, because then what you do is you have learned a model perfect for the training data, but this is not the data you want to apply it for, and so this might not be the best thing to do. And yeah, what I said already, hyperparameters cannot be learned from the data, but they have a very crucial influence. So let's look at some of the examples. Here is a tree-based ensemble. So for example, XGBoost, what you do there is you learn decision trees, or in this case, they would be regression trees because they don't give a class at the end, but they give a value. And here you see that this ensemble, it's a very small ensemble, just consists of 2 trees, but that would be, for example, the first hyperparameter to be learned or to be optimized. How many of these trees do we actually need to basically get a good signal out of the training data? And usually this is not 1, 2, 3, this is like 500, 1,000, 3,000, something like that, at least for our data. Then the depth of the tree is also something that we have to specify before. You can see on the right, this tree has a depth of 1, it just consists of 1 split. On the left, you have 2 splits. You can also learn 1 tree that has like 100,000 splits, but this usually also is not great. So this is something you need to optimize. And then also some other criteria. I don't want to go too much into detail because time is running out, but for example, when to prune a tree, if you have too few of your data instances in the final leaf, then what you do is actually you don't take that split, because you would say this overfits the training data. And some more. And then the other example, I hope you all know deep neural networks. So here we have on the left, the yellow one is some input, some features, let's say for a user, or let's say for an image or so, and we want to predict something on the right, which could be like, what do we see on this image? And each of these orange nodes then is the probability. For example, the first one is the probability of seeing a cat on this image, the second one of a dog, third one of an airplane, and so on and so on. And yeah, these kind of deep neural networks also have hyperparameters. For example, the structural ones, how deep is it? How many layers do we actually use in this network? How is the width of this network? So this would be like the height of these intermediate layers. Like, is it fully connected? Do we have sparse connections? This is something like, if you want to basically try all combinations, this is just nuts. You don't want to do it. And then also activation functions, which are used in neural networks. There we have, let's say, maybe the choice of 5 different activation functions. Which one is the best? We don't know prior to learning. And then also, again, the optimization algorithm, dropout and regularization, where, let's say dropout is also something that regularizes the model. So there you have a lot of parameters. So basically, it's like, what you can do is you can maybe understand it as like, you want to bake a cake, and you don't know the recipe, and you're just wildly guessing. Do I use this, do I use that, and you just put it in, and you can only in the end try the cake that you baked, and then you see, is it good or not. And this is kind of the analog to hyperparameter optimization. Okay, and then what do many people do? Assume that we have only 2 or only a few hyperparameters. Then what we can do is just use a brute force approach. For example, here we have 2 hyperparameters that are on the x and y axis, the gamma and some cost parameter of a support vector machine. And then we just compute the model, learn the model. Let's say these are 100 different tries. And then we have 100 different accuracies. And there we just take the one that maximizes the accuracy, which is fine, because this is very easy to implement. I just basically brute force try it. And brute force, of course, is not very hard to implement. It's easily parallelizable, but what it does, it produces so many, let's say, bad or useless computations, and is therefore very, very costly. And you can assume, or you can imagine that if you have not 2 hyperparameters, but let's say 10, then this like grows exponentially and you have to do 1,000,000 computations and nobody wants to do that. So what we do, and what also the literature in machine learning does, is Bayesian optimization of hyperparameters. What is the core idea here is, yeah, we can do machine learning and we have the hyperparameters as input and some objective function as output. Hey, so why don't we do machine learning on this kind of data again? And this is actually like, yeah, putting machine learning around machine learning. So quite a, let's say, innovative approach, but it works. And yeah, you learn models, for example, Gaussian processes here. And these, why is it called Bayesian? Bayesian is usually all the modeling that has these kind of probability assumptions about your model parameters and so on. And usually what you get in the end is not just one prediction, how good is this hyperparameter configuration going to work, but you get a distribution over it. So you also have some uncertainty about it. And this, both of these quantities are used then in the, let's say, steered search to find good hyperparameters. And yeah, I've talked a lot about it, so let's look at how would this work. So this is now assuming that we only have one hyperparameter because I can draw it better than like a 5-dimensional space. So here we have just one hyperparameter on the x-axis, and let's say it's between -3 and 3, whatever sense this makes. And we have the red line, which is actually the ground truth. So this is the how good this configuration works. And what we do is we have just a few observations. I hope you can see it. These are the black dots where we have just tried this hyperparameter and we have found a value. And what we then do is learn a model, which is in this case the black line, that tries to, let's say, predict these points. And you can see it interpolates these points, and it also has some uncertainty about this. And this is the blue area around the mean. And then what we have on the bottom is the expected improvements. So this basically tells me, okay, here I should try, let's say, -1.5, because here the value is maximized. And you can also understand this because there the mean might not be the best of what we have seen so far, but the uncertainty actually surpasses this best point that we have seen so far. So what do we do then? We get this hyperparameter configuration as, let's say, proposal, and then we test it, run it, relearn the model, and now you see that we basically interpolate this red function that we want to know about a little bit better. And now you can also see what you have all seen, the maximum is on the left, so now the model actually knows much more about this region, the uncertainty decreased, and now the expected improvement tells me, okay, go to the left and try another hyperparameter configuration. Then we do this until the function is optimized. And this is basically just for you to imagine how this hyperparameter optimization can work, and which is what I'm actually working on right now. Do you want to do the resume? Okay, so let's come to the end of the talk, the resume. What have we seen here? First, we have seen on the example of the job recommendations that delivering proper recommendations is a core task here at XING. And we don't have this only for job recommendations, but also event recommendations, members you may know, group recommendations, and so on. We have seen that we have many data sources, for example, explicit, implicit data sources, social network data sources, and then also features extracted from the job postings. So we have user features, job features, for this example of the job recommender. Then we have seen that these recommendations are like the output of a very long chain where many things are computed, postings are filtered out, or taken back in, or whatever. And we have, this is quite a problem to then also deliver these recommendations in time if you want to have a recommendation because you're clicking on it on the platform. And this challenge is met by using big data technologies. Katja has shown you the tech stack that we're using. And some of these technologies are, for example, Scala, Hadoop, Hive, MySQL, Elasticsearch, and many more. And we have seen that we can, in a way, automate the whole process. That starts at feature learning, that starts then, not feature learning, sorry, at finding the features from the Hive tables, creating a data set, learning a model on these data set, then testing different hyperparameter configurations, in the end evaluating this model versus the model that is currently working in production, and then maybe starting an A/B test if these models are too different, because then we would like to know why is this one better, or we would first know is this one better, the new one. And this is an overview of how we automate machine learning workflows at XING at the example of the job recommender. Okay, that's the talk. If you have any questions, feel free to ask.
Okay, yeah, thank you. If you have questions, please ask. And of course, we are hiring data engineers and data scientists, and we have a booth outside. Any questions?
Yeah, there's one person.
Not much, so.
No, I can't see anything. You have to step out of the line.
Hey, thank you for the great talk. I was just wondering on, I totally get the necessity why to retrain the models constantly, but how do you define on how often or how regularly you retrain them? So is it rather some kind of monitoring point where you see a model drift, or is it a rule of thumb you follow? So could you just say something about that?
So this is something that we just started a few months ago, and currently is that we go for once a month. This is something we might want to play around in the future, but currently, yeah, it's more like a rule of thumb, like let's do it once a month.
Okay, thank you.
Any other question? I don't see. No.
Okay, so we don't see anything, we don't hear anything, so thank you.